we are going to look at two different sampling distributions. One of them is X bar that we started last time, and the other one is called P hat. Okay, what are they? This is the mean, sampling distribution of the mean, and this is proportion. I'll explain in a minute. I will get to that. And this is indeed 8.1 and this is 8.2. Okay. So now two different things here. For the mean, if the population is normal, that's one option. So option A, population is normal, then X bar, the mean of all samples, is normal, having, so the population is normal, let me put also here with mu and sigma, very important. Mu being the mean and sigma being its standard deviation. Then X bar will be normal. For any sample size will be normal with the same mean, but the standard deviation much smaller. The square root of the sigma over the square root of n. And this is what the book wants to call the standard error of the mean. Fine. But this is the standard deviation. And they also want to call it, so I'm going to put it here so there is no confusion, standard error of the mean. This. It's the standard deviation of this random variable that we artificially created. It's the standard deviation, also called the standard error of the mean. Second option, let's say the population is not normal or unknown, not normal, or we don't know if it's normal or not normal, unknown. Then, if the sample size is greater than or equal to 30, this was experimentally done over the years. Now you can ask, why 30 and not 29 or 55 or 102? It was experimentally determined over the years. So if it's not normal or we don't know what, population for X, the underlying population where I'm selecting samples, if it's not normal or the distribution is not known, then X bar is still normal if the sample size that I select is more than 30 or equal to 30, and with the same thing, mu and sigma over the square root of n. Now, there is something called the central limit theorem. The central limit theorem says this: regardless of X, not X bar, being normal or not, as n increases, what is n? The sample size increases, X bar is or becomes...
Professor, you're muted.
Oh no, all of a sudden? Just now? Just now, were you able to hear what I said? Where did I lose you?
You lost us at regardless.
Oh, I'm sorry. So the central limit, so it's a limit. Central limit theorem says, regardless of X being normal or not, the underlying population where I select X from, the sample size, as n, the sample size increases, X becomes normal. Okay, so this is the theory behind the sampling distribution of X bar. And we're going to have more examples. We didn't even get to examples here. Okay. Similarly, for proportions, there are two requirements. NPQ has to be greater than or equal to 10, I'll explain again. We've discussed what N and P and Q are. I'll explain again. And N has to be less than or equal to 5%. This is 5% of the uppercase N. So that's why I needed you to remember what these represent, right? N is the sample size. P is the proportion. So the proportion, what am I looking at here? Let's say I'm trying to find the parameter called, let's say, how many, the proportion of people with dark eyes in the entire population. So I select the sample, and I see that I have X number of people with dark eyes, let's say brown, black eyes, over the sample size. So this is my proportion in the sample. This is P hat, okay? So I get a sample. I count the number of people who have dark eyes over the sample size, and I determine the proportion of people with dark eyes in the sample. Also, N is the sample size, P is the proportion, population proportion. Q, of course, if you remember, is 1 minus P from the binomial distribution. I either have dark eyes, or I don't. So Q is the complement, 1 minus P. And again, the sample size. And N, we know this is the population size. Sample size, population. That's why these are so important, because we use them over and over. Okay. So P hat will have a mean for P hat, which is the same with the population mean. And it will have a sigma P hat, which is the square root of PQ over N. You can write it P, 1 minus P over N, the same thing. So, and this will be, this distribution, P hat, will be normal with mu and this, the square root of PQ over N, and this is the standard deviation. And this is the mean. Again, all this, what is all this? What am I trying to do? Why am I looking at X bar? Why am I looking at P hat? Because eventually I want to determine the best approximation of the population mean. And you can say, but where do these come from? From previous studies. Where do these come from? From previous studies. We do the study over and over to keep up with what's happening in the world. Okay, so this is an estimate of the population proportion. But again, you can say, but that's a conflict. What are you talking about? You want to use this to estimate this, but you are using P and Q? Yes, from a previous study. Okay, same thing here. Why am I estimating? Why am I looking at X bar if I already have the mu and the sigma of the population? What's the point? Yes, these are from previous studies. So we want to see if we are still there, or it has changed, or if we get a better approximation of the true population proportion and mean. So this is the idea, and this is what we are trying to do in 8.1 and 8.2. So now I'm going to share my screen, and we'll work together on anything you want. Where is my book? I had it open. Yes, here it is. So let's go back to 8.1 because we haven't accomplished anything, meaning I was slow last time, not lazy, but slow. So 8.1 and then 8.2. Hopefully we can finish these today. That's my target, hopefully. Okay. So I think we should start again if you want, or you choose. If you already started this, and if you just want me to work on what?
Question 3.
Yes, let's start with question 3. Very good. I love it when my students are interacting, when they are talking, when they're telling me their opinion. I love that. That's the whole purpose. That's why we're here. Otherwise, you can study this on your own. Okay, so the larger the sample, of course, the more accurate the sample mean will be as an estimate, right, of the true population mean, which we don't have. We can't get to 360 million people, right? We can if we do the census, but that's once every 10 years. It's extremely expensive. So yes, the larger the sample, the more accurate what I get from the sample is, the closer it is to the true population mean. So we did that last time. Okay, so moving on. What would you like?
We could do 5.
Let's do 5, very good. You can look at your end also at the problems. Just scroll and say, oh, I want to see this. I hope you can do that. Yes, so now we know that this is the special name given to the standard deviation of x bar. Nobody really cares, but yes. So it's the standard error of the mean, right? So the standard deviation of the sampling distribution, which is denoted by sigma x bar, is called blah, blah, blah. It's the standard deviation. That's all it is. Good.
Can we do that one, number 6?
Yes, of course. Let's do the number 6. Fill in the blanks correctly, to completely, yeah. Okay. Anyone would like to read it with us or give us an idea?
I can read it.
Please do.
Suppose a simple random sample of size n is drawn from a large population with a mean and standard deviation. The sample standard deviation of x bar has a mean of
Right.
blank and a standard
So
deviation.
this is important. The standard error of the mean is not important, but this is very important to understand. It's the sampling because it's coming from samples. Sampling distribution. Okay. Ready. Oh, look at that. I can move this. Oh, nice. So the sampling distribution of x bar always has the mean the same with x. This has to be the same. Okay? And the standard deviation, remember the formula. We are talking about x bar. We're not talking about x. X will have the standard deviation sigma, but we're talking about x bar. So which one do we select?
That one's the standard deviation over the square root of n,
Exactly.
right?
Yes, also called the standard error of the mean. Okay, good. Very good. Okay. Anything, or we choose the next, or, oh, I didn't mean that.
Can we do 12?
Yeah, can we do the one we're on?
The one that we are on, and then 12. Very good. We can always go back. Okay, so all I have to do here is, it says determine mu. Anyone would like us to tell us what I should fill in?
Yeah, that's just 84, right?
Exactly. It has to be the same with a mean of x. And also remember, look at n. Very important. N is over 30. We don't care whether x as the underlying population is normal or not. Okay. Now this has to be calculated. How do we calculate it?
So that one's going to be 21 over the square root of 49.
Perfect. And the square root of 49 is?
7.
And 21 divided by 7 is?
3.
Done. Okay, let's look at 12, and then we'll come back to anything else. Let's see 12. So blah, blah tells us that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases. What did we just say about that? How is it called?
Is it the central limit theorem?
Excellent. Well done. Good. I don't know if you said
We do 8.
8. Eight. Good. Also, I would like to go back to that one. What was it? Was it 13? Because it was interesting. Okay. Can anyone help with this one?
I can read it.
Please.
Use a central limit theorem to
Good.
find the mean and standard deviation of the mean of the indicated sampling distribution.
Okay.
Sketch the sampling distribution.
Okay.
The per
Capita. Per capita. Per head, in other words. Per head. Per person.
Okay.
Yeah.
Consumption of red meat by people in the country in a recent year was normally distributed with a mean of 108 pounds and a standard deviation of 38.
Yes. Stop for 1 second because I want to show you again and again. We wrote this many times, but let me write it one more time here for this problem and for each problem, actually. Okay? So this is what we wrote, we read, or we learned from the first sentence, basically, that X is normally distributed. This is an important key with mean and sigma, mean and standard deviation. Okay, perfect. Then, using random sample sizes of 15. So this is our lowercase n, which is 15. Okay, we're asked to determine the mean. Who would like to help with the mean?
Would that be 108?
Of course. Thank you. Now they want us to determine the standard deviation of x bar, this fictitious variable that we created. Because this is the mean of each sample. So now I created a new random variable with those means from each sample. How do we calculate this? Anyone?
38.6 over square root of 15.
That's it. That's exactly it. So I have 38.6 divided by the square root of 15. Okay. So we are told, I don't have to worry, because we are told that the population, the underlying population is normal. And look at the sample size is less than 30. But I don't need 30. I can use this formula because I am told that the distribution is normal. Otherwise, I would have had to inquire. Okay, so so sigma for x bar is 9.96647. And now let's see what they want. 3 decimal places, so 9.966. Okay, so let's stop for a moment. They want to sketch the graph of the sampling distribution. So I know that for x bar, always next to the distribution that you are graphing, write the variable you are representing here, because you can present p hat, you can present x, you have all sorts of other options. So always you know what it is. So the mean has to be 108. Standard deviation is roughly 10. So 1, 2, 3, 1, 2, 3. So this, the first one, right, should be 118. The next one plus another 10, 128. The next one plus another 10, 138. And the same thing on this side with minus. So this would be 98 minus 10, 88, and so on and so forth, right? So this is what we're looking for. Something that looks like this.